How you doing today? How's PA2?
I need to do some error checking, but it might be done.
Okay, cool. Hopefully well under control at this point. Is there interest in my being available Wednesday at 8 o'clock again?
Yeah.
Yeah? Okay, I'll plan on being here Wednesday at 8. Digital Lounge, same as before. If you want to go over stuff. So I want to look at the ODPs. And then I'll talk about the quiz, and then we're going to go back to hashes. So first, the ODP that you did on Friday. This was the insert. So you were given a list of 3 nodes and asked to insert between the second and the third. And there could be stuff after that third node as well. And so your goal is to take this list and create a new node with some value that we pass to the edit function. And you want to sandwich it in between that second and third node. So we can write down, if this is pointer, we can reference this second node as pointer arrow next. And we can reference the third node as the second node arrow next. The thing the second node points to, find the next field. Well, since the second node itself is pointer next, that's the second node. If we take its next, that's the third node. And that gives us the pieces we need to insert our node into the list. So what do? We call malloc. Anytime you're creating a node, you need to call malloc. If you're not creating a node, don't call malloc. If you're going to say previous equals list, you don't have to say previous equals malloc and then previous equals list. That's actually creating a memory leak, right? Call malloc if you want to create a chunk of memory that you're going to put some stuff into and do something with. If you just want a pointer to a struct node star pointer. If you want it to be equal to LL, pointer equals LL. Okay, but in this case we are creating a node, so we call malloc, and I'm saving that in a temporary variable called temp. So this is temp. And we're going to set temp arrow data equal to num. So that happens on that second line. And now we need to set up a pair of pointers. So the first thing we want to do is have temp point to this thing. Okay, so to create this green link, temp arrow next equals pointer next next. And this is the point where it can be potentially confusing, because you might think I want temp to be equal to pointer next next. But if I do that, temp is going to refer to this node. Okay, I don't want to set temp to equal this node. I want temp as a node to point to this. And the thing that temp points to is given by its next field. And temp's next field I can reference as temp arrow next. So temp arrow next equals pointer next next. That sets up that green link. And then we want to take the prior node and have that point to temp. Well, the prior node is pointer next. But if I say pointer next equals temp, I'm going to set the next field of this node. That's not what I want. I want the next field of this node. So it's actually pointer arrow next equals temp. And that can also look confusing, because I thought this was pointer next next, so am I setting this equal to temp? Go back to pointer next. That's this node. Set the next field equal to temp. That's the purple arrow. Yeah.
What about I say pointer next equal temp first, like instead of the temp next?
If you say pointer next equals temp, and then you say temp next equals pointer next, this is now equal to temp. So then you're going to be saying temp next equals temp, and you're creating a circular link to yourself. So the order definitely matters here. Okay. The other thing I could do is I could save pointer next into some other temporary variable, and then do this, and then set that equal to the temp. So different ways to do it. So temp next equals pointer next, and pointer next equals temp. You could also simplify this by doing something like previous equals pointer next, which makes this previous. And then your statements are a little less complex, right? Temp next equals previous next equals temp. And that's more the form that we're probably used to. And nothing wrong with using a temporary variable there. So lots of different possibilities. All right, so on to ODB 213. Yes, we did skip 211 and 212. We'll come back to them later, maybe. So this is a hash ODP. So we're taking a string and we're hashing it using one of the hash functions we talked about last week, which is just add up the ASCII code for each character in your string. And when you're done, we're reducing modulo 31. So if you hash the string consisting of a single character A, that has ASCII code 65. When you add up the ASCII code of all the characters, you get 65. 65 mod 31 is 3. It's got a remainder of 3 when you divide by 31. So your hash function on just an A should return a 3. ABC, if you add up the ASCII codes reduced, you get a 12. So the hash of ABC should be 12. And there's a few strings in here with sample hash values that should be returned. And the function you're writing is just called hash. Takes a character pointer, that's a string, and returns an int. And if you want to test your hash function, you can do something like this. Right, one print statement. Print ABC hash is 2% D, and for my argument, I'm just going to call hash of ABC. And that should give me a 12. And if I say hash of hello, that should give me whatever value the README says hello should hash to. And that's a really straightforward way to test your hash function. But you may choose to test it by writing a more general program that lets you type something in and then hashes it. And there's a cautionary note here in the README which says be careful if you're reading with fgets. Remember, fgets adds a new line to the end. So if I say something like fgets string 120 standard in, and then I hash str, if I type in the letter A and I hit enter, str is not the letter A. It's the letter A followed by a new line. And when I call my hash function, it's not hashing a string containing just the letter A. It's hashing a string containing the letter A followed by a new line. ASCII code of a new line is 10, so all my numbers are going to be off by 10. And A is going to hash to 13 instead of 3. ABC is going to hash to 22 instead of 12, and so on. That is not a problem with your hash function. Okay, don't try to tweak your hash function to deal with that. Don't stop hashing when you see a new line. Don't choose to ignore new lines, things like that. Hash function reads everything in the string, adds the ASCII codes, reduces. Okay, if you want to get this to work with your main program and you want to actually type in an A and have it hash just an A, what you can do is get rid of the new line after you call fgets. So suppose you type ABC, and fgets adds a new line before the null terminator, and you want to turn that into just ABC followed by the null terminator. Well, we can do that ourselves. All we need to do is figure out where this new line is and replace that with a null terminator. So how do we find a new line?
Search for like the new line ASCII code?
We could search for it. There's a easier way, a lazier way that doesn't require looping.
Maybe string length?
Yeah, we know that the new line's always the last character in the string. So if we call string length, that'll tell us how long the string is. We can figure it out from there. So ABC new line, what's the string length of that?
4.
That's 4, right? String length does not count the null terminator. 1, 2, 3, 4 characters. What's the index in this string of the new line? The index is actually 3. And if you do a few test cases, you'll find the index of the new line is always 1 less than the string length. So we can do something like this. And again, there's multiple ways you can write that, but this is taking the length of the string, subtracting 1, and then setting the element at that position equal to the null terminator. That clobbers the new line, assuming it clobbers whatever the last character is in the string, which for us we're assuming is always a new line. So if you were to do this and then call hash of string, you can type hello and you should get back what it says hello hashes to. Or you can just, call it directly. But that's a useful exercise anyway. All right, so any questions on 213? You're really just writing a loop that goes through each character, adds them together, and then mods 31 returns the end. So 214 tomorrow is exactly the same, except it adds a probe. So your hash takes 2 arguments. The second argument is the probe number, and I think the hash function is to add the square of the probe. So it's one little tweak at the end of your loop, or the beginning. All right, so next order of business, I opened up a quiz for 222, and the quiz is due on Wednesday, and it's 5 questions, multiple choice, so it should not be a real big deal. So this is quiz 2. And read through it, see if it makes sense, and if not, bring questions to class or post on a discussion. But, if you declare integer x32, what does the symbol x actually refer to? Here's a y equals star x, and if we said these things beforehand, then what does that y equals star x do? So it's stuff that we talked about first or second week, just sort of some refreshers on pointers and structs and addresses. And good old seg faults. So take a look at that, and it closes Wednesday, I think at midnight. But my suggestion: do this today, and if any questions come up, bring them to class tomorrow. And I don't think there's a time limit, and you can retake it as many times as you like. So that's quiz 2. Wednesday, I'm going to open up this GDB quiz. And it's a quiz that uses a set of code that's sitting on the Linux server and requires you to run GDB on it and then basically do some analysis on the memory, the structures, figure out where some things are stored in memory, how big some things are, and so on and so forth. So it's a kind of forced application of GDB to explore what's going on inside the computer. I'd like to spend some class time on Wednesday having you do this in groups. So if you have a laptop or a phone or tablet that you can do Linux on, definitely bring that in on Wednesday. And you can work in groups. Okay, I'm not going to specify group sizes, but particularly if you don't have equipment you can bring in on, you're definitely going to want to work with somebody who has a laptop or other device. But we'll spend some time, we'll put the quiz up here, and you can work on it and I can answer questions and so on. But I want to make sure that people are definitely getting some hands-on practice with GDB, because when we get into trees you're really going to have to rely on it. So we'll do that on Wednesday, and you can do the GDB quiz on your own if you want, right? It's not something you can only do during class time. I'll leave it open probably through the weekend. So come in and work on it in here, but if you prefer to also work on it on your own, you can do that as well. So I'll open that Wednesday, and we'll talk about it then. All right, questions so far, any of that? Okay, abstract data types. So we've talked about the general idea of a hash, associative array, key and data pairs. We looked at some pseudocode, implementation of fetching and deleting, and some of the details of deleting and remembering that you deleted, and so on and so forth. And we've talked about hash functions a little bit. I want to take a step back and look at hashes from a user perspective. And so this is the idea, again, of an abstract data type. We've been talking about hash. Here's a hash function. We've got an array, and there's a valid field and a deleted field. Those are implementation level issues. I want to step beyond all of that and say, suppose you're just a user and you're trying to use a hash in your code. What does your interface to this hash look like? And as a user, we don't care about deleted flags. We don't care about arrays and fields and structures and all this kind of stuff. We care about something very different. So some sort of initialization, some way to say, hey, I'd like to start with a hash table, right? So do some setup. We'd like to be able to, so this is pseudo-ish pseudocode, but HT is our hash table, whatever that is. So we do some initialization and we get an empty hash table. We'd like to be able to store, and we'd probably specify what the hash table is. And then basically we need a key and a data pair. So some kind of key and data. And maybe they're strings, maybe they're structures. But abstractly, right, this is how we store something. We say, here's the hash table, here's a key, here's a piece of data. Store that pair of things in the hash table. And typically, if the key is already in the table, it will replace it. Okay, we'd also like to be able to say fetch. So give it a hash table and a key, and have fetch tell us what the data is associated with that key. And we'd like to delete. And usually we delete based on key. Maybe not usually, but in this case, here's a key, go ahead and remove that and the associated data from the hash table. And that's a fairly complete set of interface functions. Because what do you do with a hash? You store stuff, you fetch stuff, you delete stuff. That's kind of the basic modality, right? So you're making a table of directory information. So here's a person's name, here's their office number, here's their phone number, here's their department, right? So store all that stuff associated with the person's name. Or fetch all that information for this person, or this person has retired, delete them from the database. So there's one other thing that we might want to do that we cannot do with these functions. And that is show me everything that's in the hash. Give me access to all the information that's in there. Give me a list of all the keys, for example, all the names of people that are in this hash table. Because the only thing we can do to fetch from a hash is give it a key and say, give me the data associated with that. Well, if we don't know that Izod is a key somewhere in the table, we can't access Izod's data. We've got to know that we should say, hey, fetch the data for Izod. And this is a peculiar problem, right? We don't have this problem with arrays. If you have an array of n things, we can make a for loop for I equals 0 to n. Give me element I. And that will loop through. It'll give you every element in the array. If you have a linked list, we can say, hey, give me the first node. See what that points to. Give me that node. See what that points to. Give me that node. And keep going until you're null. And you'll get every node in the list eventually. With a hash table like this, we don't have that ability. And you may be thinking, well, the hash is stored in an array, so we can just go through the array and check the valid flag, and if it's valid and not deleted, give you that key. But we don't know any of that stuff as a user. Okay, that's the implementation level. This is the abstract user level. And we don't want the user to have to go down to that implementation level. Because today we're using an array with a valid flag. Tomorrow we might be using a linked list with a present flag. And suddenly the user's code breaks because we changed the structure underneath. So we usually have a pair of functions that implement something called an iterator. And this is a general notion, and we'll talk about iterators a lot in 223. An iterator is, roughly speaking, it's a way to do what we're describing, to get access to all the stuff that's in our data structure, one piece at a time. And iterators usually work as a pair of functions, so we could have something like get first key, so we could say get first key and pass it the name of the hash table, and it will return to us a key. Now, what makes a key the first key? Who knows? It might be the first thing in the array. It might be the shortest key. It might be the last key that was stored. No guarantees, right? To the user, it doesn't matter. I just want a first key. And we can take that key, we can say fetch the data, we could print out the key data pair. Okay, if we want another key, we can say get next key. And usually, sometimes you might also have to specify the last key that you got. And it will say, okay, here's a new key. Sometimes it'll do that housekeeping internally. So we say get next key, and it gives us another key. And we can fetch the data associated with that, print it out, and we can say get next key. And so we can put this in a while loop. And usually, key will come back with some peculiar value like null, which tells you that you've gotten all your keys. So you can make while key is not null, or whatever the iterator is using to indicate that. So with that pair of functions, now we can go through, we can basically dump out the whole hash. We can get a list of keys one at a time. We can fetch the data for each key. Does that make mostly sense? So let's look at some code for this. So there's a package called DBM. It's a database management package. It's basically a hash table implementation available in C. And the version that you find today is GDBM. It's the GNU DBM. And if you look at the manual page, it's got basically these functions that we were just talking about. There's this open function, that's the initialization. Okay, that creates a hash table. You give it a name for the hash table. Block size is just how big a chunk it's going to use, so we just usually use 512. Some flags that tell it how we want the table created, permission modes, same thing you'd use on a change mode, and so on. So you open a hash table with this, and it gives you back this thing called a GDBM file. Okay, that's a type def somewhere in this include file. And then if you want to fetch, you say GDBM, whatever the name of the hash file is, and then you give it a key, and it returns a datum. So you could hash on integers, you could hash on strings, you could hash on something else. So instead of saying that this expects a key, which is a char star, it's a generic type called a datum. And it's a structure, it's type def, right? And it has two pieces. It has a pointer to the actual data, and it has a size, how many bytes it's pointing to. So we're going to use this to store strings and retrieve strings. But just think of it as a generic type of thing. So fetch takes a key and it returns a piece of data. Delete takes a key and deletes it and returns some kind of flag. And store takes the hash table, it takes a key and it takes the piece of data associated with it. And flag lets us say whether we should replace something if it's already found in the table. All right, and then here's the pair of functions that implement the iterator. So we can ask for the first key, and then we can pass that key and ask for the next key. And that'll let us iterate. And we don't have to worry about these other things. And this is a fairly big package. It's got a lot of stuff going on. So I've posted this code on Canvas. There's a link to course code. So under 222 GDBM, you can find a copy of this. So this is a test main program to let us play with these functions. So we include GDBM up at the top and a few other things. And DB is going to be the name of my hash table, which is basically a database. So that's the DB part. And then key and data are just temporary variables for keys and data. Some temporary character arrays and so on. Okay, so opening a hash table, so GDBM open. So database is the name of my hash table. And the system is actually going to create a file in my current directory named database, and that's where it's going to store all the information. 512 is a block size, that's just standard. GDBM reader, ORed with write create, so I want read and write access to this. And if the database doesn't exist, I want to create it. So that's what those GDBM underscores do. 600 means I have read-write permission, nobody else has access, and the flag is just 0. So that creates a database. And then I've got a little main program that's going to let me type in commands, and it's going to interact with this hash table. So I print out a prompt, S to store, R to retrieve, D to dump, Control D to quit. So I do an fgets, get this input stored in buffer, and then I switch on buffer 0. Okay, this is very much like PA1, PA2 main program. Same kind of thing. We're going to see this a lot. Do a prompt, read some input, do some parsing on it, and then take some action. So our parsing is very straightforward here because I prompt for everything. So if your first character is an S, we're trying to store something. So I print out a prompt, says enter the key. I read a key from the user, and then I set up this datum called key with these two lines. The data pointer I set equal to the address where those input characters are stored, that's buffer. And then the data size I set to the length of the input string plus 1. So if the user types in ABC, string length is 3, I store a length of 4. Why? Because I want that null terminator. Right? And there's nothing magic about this interface that says I'm going to put null terminators on your data for you. Okay, it'll do exactly what you tell it to do. So if I actually just stored 3 things, I'd store ABC, and that would be it. And then if I wanted to print it later, I'd have to put a null terminator on the end. So I store the length plus 1, and I'll do that everywhere. So then I ask for the data, same thing, get the data, set up a datum called data. So now I've got a key data pair in these variables, and we just call the store function. So there's a database, the key, and the data, and I have a flag saying if it's already in the database, replace it. And that's it. We've stored our key data pair now, so we can break. If you say retrieve data, same thing, ask for a key, read it in, set up the datum pointer and data pointer and size, and then call fetch. So fetch returns a data object, and if the key is not found, it'll return an object with size 0. So if the size is bigger than 0, I go ahead and I print it out. How do I print it? I just take the D pointer and I use a %s. Otherwise, I'll print an error message saying the key wasn't found, and then either way I just break. Okay, if you want to dump, call the first key, that gives me a key, and I make sure that the pointer is not null. That's how I know that I've gotten all the keys. So if the D pointer is not null, I'm going to go into this while loop, fetch the data associated with the key, print it out, and then call next key. There's my whole loop. Okay, all the hard work is being done by these routines. We're just using an interface to all of these functions, and we want to store something, we call store. We want to fetch, we call fetch. All right, and then when we're done, print a prompt, and that's the end of our code. Go back up to the top. When we exit the while loop, we'll call close, just to close out the file and exit. So this is just test code, right? But let's see what this does. So if I compile it like this, I'll get errors from the linker, because by default, all of these functions aren't automatically included. Just like square root. If you put a square root in your code and you just say GCC, you get similar looking errors. You have to tell it where these functions are. So at the end of your compile, you say -L GDBM. That's the name, part of the name of the library where these functions are stored. That lets you compile. All right, so let's run main. So if I say dump, there's nothing in my database yet. Okay, so let's store. So key will be Nick, and data will be CS teacher. Okay, let's store Izad, and data will be tons of experience. Spelled wrong, but Izad is the person I go to when I have any questions about anything. So store, let's have the key dragons, and what data do we associate with dragons?
Who's wrote down?
What? I didn't hear what he said, but it sounded good. So bring marshmallows, also spelled wrong. And right, so there's a really strange key, and you know it can have whatever associated with it. I'm not going to be able to retrieve that because I can't type that in again. But I can say dump, right, and show me everything that's in my table, and there's a complete list of all the key and data pairs. And it's not in order in some sense, right, because I put in Izad before I put in dragons, but dragons came out first. That's okay. There's nothing about these iterators that say you're going to get these keys in a particular order. And that's typical of iterators also. So, and I can fetch, right, retrieve Izad, right, so there's Izad, and I can store Izad and put in something different, and now I've got different data associated with Izad. And this has created a file called database, which if I look at it, it's mostly hopeless. But it's persistent, right? Because it's just a file on disk. So now I can retrieve Nick, and there's Nick's information. And I can dump and everything's still in there. So this is a useful way to make persistent information that you want to have around from run to run. So for some reason this launched me into a bit of a tangent earlier, so I'll do it here also. How many people here play Rogue? Oh, the same underwhelming response. Okay. So if your productivity drops to 0, don't blame me. So Rogue is a little dungeon adventure game. Brings up a picture of a map. You're the little character with the @ sign. You can move with HJKL, right? So this is good VI practice. So I'll move L and go across. And there's a mace. That's a useful weapon. There's some gold. And these pluses are entrances to tunnels. And so you can move across until you either hit a dead end or a corner or you get into another room. And there's a room, and I'm being attacked by an emu and a kestrel, which is probably not good. So I'm going to back off into the tunnel so I can fight these one at a time. And I defeated the emu. I'm down to 7 health points. Hey, I got the kestrel, good. There's a potion, and so on. So you can just kind of play around. But I should have let myself die. I need something that'll kill me. There's a snake. I didn't want to do that. Okay, this'll kill me. I'm just going to hang out here while they beat me up. There you go. Okay, so I got killed by a kestrel. I had 16 gold. So this will also show you like the top 10 scorers, right? And this file is maintained on the system. These are actually mostly players from last year. So you have to like get your names up here.
Is this a program in your database?
This is on the Linux server. But the reason I got onto it is because if you wanted to do something like store player information that you can retrieve at the end of the game, you could do that with GDBM. Right? You could make a hash table where you key on the username of a person and you associate with that a piece of data that has, you know, how they died, what level they were on, what their score was at the end. And then if you want to pull out somebody's past history, right, you can just go in and fetch based on their username. And because it stores it in a file instead of just storing it in memory, it's persistent. And so these are, you know, a year old, but they're still there. But anyway, so that's Rogue. It's a good way to detune your brain if you're stuck on a problem. You can go fight some kestrels and emus in the dungeon and then come back and be successful. All right, so the other thing I wanted to mention along the lines of this, so GDBM is installed on the Linux server. It's already available. On my Linux machine, I did not have access to GDBM. It didn't exist. Okay, now some packages you just go to the software center and you download and it automatically installs everything for you and you're good to go. But a lot of stuff, especially older stuff, you might have to install yourself. So I went to a website and found GDBM's tarball, so a tar.gz file, it's called a tarball, and downloaded that. And you have to install that. So let me show you what this process kind of looks like. And up front I'll tell you, you only want to do this if you absolutely trust the integrity of that file, right? Because you're basically going to be running a bunch of code that you don't really know what it does. But I trust the integrity of this file. So I'm going to make a new directory. I'm just going to call it source. And I'm going to do everything from that directory on down. So I'm not going to mess with any of my code up here. So I'm going to cd into source. And first thing I'm going to do is extract everything from this tarball. So tar extract verbose file, name of the tarball, and it creates all of this stuff. And typically all this stuff will come in under a subdirectory, so all of these are located under GDBM 118.1. So that's the only thing in this directory. I can go into there and I've got a bunch of stuff. And there's a directory under here called source, and if I look in there, there's the source code for GDBM. And you can look at it. You can look at hash.c, that's the hash function. It's 60 lines, but it's filled with magic numbers and modulo 24 and index times 5 and weird calculations and stuff like that. This is its hash function. Right? Why is it doing that? Who knows? But it's just C code. I can change this. I can tweak it. I can modify it. This is a copy sitting in my directory. Right? I'm the owner of it magically because I'm the one who untarred it. And you can modify it. Right? This is the whole nature of open source stuff. If you don't like something about this, you can change it to something you like better.
Provided you know how.
Provided you know how. And figuring out how is a really, really excellent way to get better at programming. Right? So one of my early hacks was on Rogue, actually, because there used to be a God mode. You could do a Control-G, and if you put in the right password, it would put you into God mode, and you could create objects, you could go up and down stairs, and you could wish monsters away with a command and all kinds of stuff. And once I got the source code, it was like really easy to. All right, so let's go back in here. And if I say make, it doesn't work because I don't have a make file. I have a make file am and a make file in, but there's no just plain old make file. Okay, so typically when you're going down this path, what you have to do first is something called a configure step. And the idea of configuring is basically when we create makefiles, when you create a makefile, you're doing it on the Linux server. When I take that and I say make, I'm going to be doing it on the same Linux server. It's exactly the same environment. So we don't have to worry you're using one version of GCC, I'm using a different one. Right? Or you're expecting some library to be present and I don't have it on my system, right? Everything's tightly controlled. But something like this, which is sitting on a website and anybody on the planet might download it, and you might put it on your Raspberry Pi, and you might put it on your supercomputer, right? You've got to make sure that certain requirements are satisfied, and so on. So configuration basically takes care of that. So here I'm just going to say configure, and configure is 17,000 lines of shell script. Okay, I don't know what it does, and if I don't have a good reason to trust that this is safe to run, don't run it, because in 2 lines of shell script, you can do some really nasty things in 17,000 lines, right? So, but I'm the trusting type, so I'm going to say configure, and it's checking for a bunch of stuff basically. And I don't know what any of that means, but I didn't get any error messages, so I'm happy about that. And now if I do an ls, hey, I've got a make file. Okay, so it's decided that my system is worthy of being able to make this. And the make file itself is close to 1,000 lines. And it's got functions, and it's got if statements and case statements and tons of variables that are set up. And I don't know what any of this does either. But again, I have faith that if I say make, it's going to make this. So I'll say make. And you can see it's compiling some stuff. And this can take, a day if you're building something big like Linux. This is pretty small, so it takes, a few seconds. And no error messages. And now if I look at my source directory, I've got a bunch more stuff. I've got a bunch of .o files. I've got some .lo files. And presumably it's compiled and linked everything together, and I've got all the pieces of GDBM now. So we downloaded, extracted, configure, make. But everything is in my directory. So the last thing you need to do is actually install this. You need to push it out so that when I say man GDBM, the man pages are in the system location where manual pages should be stored. When I say -L GDBM, the library is in the system location where libraries are stored. So if you say make install, typically it'll fail. And the failure is things around this, permission denied. Why? It was trying to remove a file from a system directory, and you can't do that as a regular user. Okay, well, this is my machine, so I can say sudo and say do this as a super user. Put in your password, and now it should succeed, no error messages. And so now GDBM is installed on the system. So that's kind of a typical tool flow that you go through when you start with a tarball and you're trying to install, whether it's a driver or some kind of package or library or things like that. In the past, at least, more often than not, when I would try to do this, it would fail somewhere. And then you end up going into the source code or maybe the make files and modifying stuff. Because, you know, this may have been written 5 years ago, and the operating system today may be different in some fundamental way. And it may be that they were assuming that, you know, a certain library existed at a certain version, and maybe that's been changed. Or maybe the name of some function got changed, and you might have to end up going in and doing some tweaking to the code. And that's part of the fun / frustration of dealing with these. But anyway, that's kind of the low-level version of installing something. Not something that you're going to have to reproduce for a test or anything. And the details of GDBM are not something that I'm going to ask you about on a test or anything, but I want you to be aware that it's available from C. We have hash tables available in Java in a lot of different forms, and it's very straightforward to use there. But if you're in C and you really need something like this, it is out there. So that sample code is on the web page. You can get to from Canvas. GDBM's installed on the server. If you feel like messing with it, it's another one of these really useful tools that once you sort of know how to use it and it's in your brain, you'll start finding applications for it. Kind of like 3D printers. You can live without them, but once you have one, like, you can't imagine not having one. All right, so bring questions tomorrow on ODP or PA2, and after questions, we're going to start talking about stacks and queues. So that'll be our next topic, and that'll take us into PA3.